let's talk about the idea of general solutions. So consider this differential equation, dy dx is equal to 6x. And the solutions to this differential equation are, well, you can quickly think of them. So one would be 3x squared. Another one would be 3x squared plus 1, or 3x squared plus 2, or so on and so forth. If you were to plot these, by the way, they would look something like this. You would have the solution curves, which look like this. So that's 3x squared, or 3x squared plus 1, and so on, which these different solution curves, solutions to this differential equation, are just translations of the solution up and down. Okay, so what about in general? Well, in general, you could have a solution that looks like 3x squared plus c. And that would be a solution for any value of the constant c. And so this is what we call then a general solution. And so a general solution to some differential equation is then a solution which has one or more arbitrary constants in it. By the way, we should note that the solutions y of x is equal to 3x squared plus c, actually, we say that this is an infinite family of solutions, because there's not just one solution, and there's an infinite number of solutions that you could choose, all of which satisfy the differential equation. Okay, so let's consider an example where y of x now satisfies the differential equation dy dx is equal to minus 3. Okay, straightforward differential equation. So what would a solution look like? Well, at least one solution would be minus 3x. That clearly solves it. How about a general solution? What would the general solution look like? Well, you can kind of quickly guess that you can translate the solutions up and down, and so minus 3x plus c should be the general solution to this. All of these solutions would have dy dx equal to minus 3. What, for instance, would the value of c be if y at x equal to 0 is equal to 7? So we plug that into our equation, and we find that c must be equal to 7 in that case. So we say y of x would then be minus 3x plus 7 when we impose our initial condition. And this is pretty general. The arbitrary constant or arbitrary constants in your problem, in your solution, are going to be determined by your initial conditions. But before you impose your initial conditions, you know nothing about them. You have to leave them fairly arbitrary. By the way, this is a good moment to talk about terminology. There's something we call an initial value problem. And the initial value problem is a combination of a differential equation, say dy dx equal to minus 3, and an initial condition like we just had, y at x equal to 0 is 7. So again, in general, it's a differential equation combined with some initial condition is what we call an initial value problem. Okay, so let's look at another example. Find the general solution and the particular solution to the initial value problem, or IVP, of dy dx is equal to y, and y at x equal to 0 is equal to 10. So let's look at a solution for this. Well, it's pretty quick to see that y equal to e to the x is a solution. How about e to the x plus c? Is that the general solution? It certainly has an arbitrary constant. But check it. Plug it back into your differential equation. Dy dx then is equal to e to the x, but y itself is e to the x plus c. So dy dx is not equal to y in this case. So that actually is not a general solution. How about c times e to the x? Is that the general solution? And it's straightforward to see that, yes, indeed, this is the general solution. Namely, it solves the differential equation, and it has an arbitrary constant, so it must be the general solution. Let's impose some initial conditions on this differential equation and this solution. So let's say y at x equal to 0 is 10, which then, of course, tells us that c must be equal to 10. And so we then say that the solution to the initial value problem is dy dx is equal to y, and y of 0 is 10. That solution is just 10 e to the x.